But this is where it's so nice to have that half-hour gap between classes. So.
I'm thankful for it too.
Yeah, I bet. Okay, so I guess the logical thing to deal with first is, does anyone have any questions about homework?
Maybe one.
Okay.
I can ask it later if you prefer.
Oh, well, it might be in general interest. And
So I noticed, and I didn't notice until I started working these, you would mention listing linear, what the linear combination would be for P for
Yeah.
the particular solution.
Yeah.
So, but you said to go ahead and exclude your like
A homogeneous solution.
the homogeneous solution.
Yeah.
But there were sometimes we should have. I'm trying to find these are so out of order. But sometimes within the linear combination, there might be an exponential term, and I don't think it's part of the homogeneous term, and but I should list that, correct?
Okay. Well, it depends. Like if it's the exponential, so e to the pt times a constant, then that's a homogeneous solution. So you would not include that. But you can have, and I believe one of the cases brings it out, if it's e to the pt times a function of t.
There's one where I got the AT, so where A doesn't equal P.
Oh yes, yeah, so that's included. So
okay, that's what I'm asking about. Yeah.
Yeah, so now, in this case, okay.
I hope I'm not doing stuff wrong because I've been doing these very similarly.
All right. Oh, but then, let me check the rest of this then. Oh, yeah, C instead of P, okay.
Oh, yeah, sorry. I've been using C as my general constant.
Okay, so what we need to keep in mind, though, is, okay. So here you have e to CT times all of this.
Right.
You forgot to distribute the e to CT to here.
Oh, yeah, that could have been just a careless error. I've generally been distributing it, but
okay. Yeah, so then you wouldn't have a 1.
Yeah, I forgot to distribute it, right? I'm glad, that worked out.
Yeah, and all that. So this is actually a very common mistake when you're applying these solution formulas and you have this exponential sitting outside the integral. And when you work out the integrals, got multiple terms, and you got to remember to distribute that exponential to all the terms.
Right.
So I'll make sure that you guys keep that in mind too.
So this one should just be e to the at because I wouldn't include the e to the ct since that's my.
Right.
Yeah. Okay.
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 Yeah,
I'm gonna have to check through those, I suppose, because you're all mistaken.
Yeah. Okay. So anyone else? You guys have any questions? They're moving along okay, or not started yet, or?
Yeah, I haven't started yet, so I don't have any questions. Yeah, Wednesday is my day to go into campus and teach, so I haven't begun it yet. I'll probably start it tomorrow.
Yeah. Okay.
I was about to say, yeah, I haven't really started it either. I know Walker had reached out to us, and it's been such a week that I feel like I'm behind on like absolutely everything already, and it's only like week 3. So I've been playing catch up in like my other class, and then this one is like next to be kind of caught up on.
Yeah. Okay, that's fine. Well, apparently for Walker it didn't take very long, right? Okay, so no problem that.
It's like a little lengthy in that there were 10 problems, but it wasn't.
Yeah.
It was the same process, so at least it wasn't something new and challenging in that sense.
Yep. Okay. Okay. Okay.
I don't think my student read my message. I
Oh.
told him that he needed tomorrow to pick up his computer. He left, but he's like, on my way. And I'm like, won't be there. I said I'm in class. But
Students just never listened.
I suppose sometimes I could have walked in there too, but I just, we'll figure it out.
So, so far, I've only dealt with first order equations, but really the aim of the course is to develop solution formulas for higher order ODEs. And the way that's done is to treat them as systems of first order equations, and use what we've just seen on how to solve a single first order equation, generalize it to systems, and then that can be used to solve higher order equations. So now I'll start getting into systems, which is where things start to get a little bit linear algebra-y. So I have no idea how many classes periods it'll take to get to my goal, but as you can see, I have no notes, but we'll just see how things go. And if I happen to think of a homework problem along the way, then okay, but right now I can't fathom what that would be. So, okay, this is annoying. All right, so, okay, so the real goal, solution formulas, or a sample PDE, y double prime plus py prime plus qy is equal to g of t, where p and q are assumed to be constants, and then you have appropriate initial or maybe boundary conditions. Like it could be initial conditions on y and y prime, or two conditions on y, like at boundaries like a and b. Either way. So now in a first course on ODEs, methods for solving this are taught, doing the characteristic equation, and then when you have g of t non-zero, you have methods like method of undetermined coefficients, variation of parameters. So the goal in this class is to show where all those come from, like rigorously deriving them, and relating them to what we see from first order equations by way of linear algebra.
So integrating factor, is that only, I should already know this, but is that only for linear?
Or first order?
First order, sorry. Not linear, first order.
Yeah, so it would be first order, although it could be for a single equation, which is what we've seen, or for a system. You can have an integrating factor. If it's a system of first order equations, you can do an integrating factor for that, but the factor would actually be a matrix. But this is what we'll come to.
But second order, you can't.
Not the way it's written, but that's why we're not really going to work with it in this form.
Okay.
What we'll do is I'm going to show you how to rewrite it as a first order system, which actually you would have seen in Math 605.
I can't remember. It's fine.
That's right. Well, it was about a year ago. So
is that generally always going to be the goal, is to get it to a first order? I guess I recall doing something.
Yeah, because you can always do that.
Yeah.
And there's so much more known about how to do first order equations.
Right.
And we're most interested in first order systems that come from these higher order equations. but certain things I'll show you can be apply in general.
Yeah.
So then what we'll do is we'll solve a first order system, and then we'll put it back in these terms to have the actual solution formula.
I remember this kind of now. Okay.
Okay. All right. So if I let u1 equal to y, u2 equal to y prime, then a first order system would just have equations for u1 prime and u2 prime. So u1 prime is u2. That's just saying y prime equals y prime. And then u2 prime would be equal to, if I took all this stuff and moved it to the other side, I'd have minus q u1 minus p u2, and then plus GT. All right. So now we have a first order system, and then if you have initial conditions for y and y prime, those would be initial conditions, same initial conditions for u1 and u2. But then what I'm going to do is express this system in matrix vector form. So u1 and u2, the whole thing prime, but that's just a vector u1 prime, u2 prime, is equal to, and then in the right side, if I see what is multiplying u1 or u2, those are matrix entries. So like in the first equation, I only have u2, so I'll have 0 and 1. And then for a second equation, I have minus q u1 and then minus p u2. And then I have this vector off to the side that accounts for the source term g of t. So now I have u as a vector prime is equal to au plus b of t, where that's a vector quantity. So b of t is a vector that has 0 for a first component and g of t for a second component. So now this is an equation that's the exact same form as what we've just been doing, where we had y prime is equal to py plus q of t. It's just that now the solution is a vector, and this coefficient is a matrix, and this other coefficient is a vector also. So what we'd like to do is have a solution formula for this that's similar to the solution formula we have for a case of just one first order equation. And you actually do arrive at that, and they have exactly the same appearance. It's just that you have appropriate generalizations to vectors and matrices. But what I want to do here is not just write it down and say, okay, that's it, but build all that from the ground up. So starting exactly where we were at with single equations and use linear algebra to bridge the gap from there to here. So, so what I'm going to do now is, well, okay, actually this is a good point to stop with this board. Because here I have a first order system of two equations of a particular form. But now, of just two equations. So now what I want to do is look at a general first order system. and see what can be done. All right, so okay. So we have y prime is equal to ay plus b of t. So same form. So but A can be just whatever square matrix, and b of t is whatever vector valued function. Okay. Now, I'm going to assume, well, okay. I assume that the matrix A, the constant matrix, is diagonalizable, which will not always be the case. In fact, we will have to deal with some cases where it's not. But for now, we'll assume it is. So that means that there exists a invertible matrix P such that P inverse AP is equal to some matrix D where D is diagonal.
The diagonal, and that's where the entries down the diagonal
Yes.
are.
So all entries are 0 except
For the diagonal.
yeah.
And does it necessarily have to be 1, just like the eigenvalues, or it has to be 1?
Okay.
Or I'm thinking about the identity, I'm sorry.
Okay. So I'll write the structure here. So D1 into Dn.
Right.
Everything else 0.
Right. So just there's entries down the diagonal.
Yeah. So if I had a 2x2 system earlier, we'll assume any size here. Okay. So now what I can do is really change a dependent variable. Okay. Find a variable w. The oh wait, not P. Yeah. Okay. So W is find to be P inverse times Y. So then what I'll do is multiply my system of ODEs on the left by P inverse. And then, before I continue, after A, I'm going to write P inverse, because that's identity anyway, Y plus P inverse P of T. Okay. Now, group all that together. Now, oh, it should be Y prime. Okay. Now, what I could do on the left side is I can move a P inverse inside the derivative. And the reason I can do that is because P is a constant matrix. So if A was a matrix whose entries are functions of time, I could not do that. And then the right side, P inverse AP is, well, this is W prime. Now, that's why I did that. And P inverse AP, that's D. And then P inverse Y, that's W. And then P inverse B of T, I'm going to call C of T. So now, I have a system of ODEs that has the same appearance as the original. And Y prime is AY plus B. Now I have W prime is DW plus C. Except matrix D is diagonal. And the reason why that's so important is now suppose I write out this system of equations one equation at a time, so component by component. So I have W1 prime is equal to D1W1 plus D1 of T. W2 prime is D2W2, and so on. In other words, each one of the new unknowns, W1, W2, etc., can be solved independently of each other. Whereas if I were to write this system of equations now, component by component, I'd have like Y1 prime is a linear combination of Y1, Y2, etc. We'd have a full matrix vector product. And we'd have n equations that are coupled together. So I could not solve them independently.
Okay, where did the C come from?
What?
The C?
Oh, C is equal to P inverse B.
Okay, I didn't know if I assumed so.
Okay.
We didn't say, you may have said it. Or,
I might have, yeah.
Okay.
I should have.
okay.
Yeah, so just
We're
whatever
just
source.
calling that.
Yeah,
Okay.
yeah. At least we know how to solve. So we have a solution for that already. So let's go ahead and fill that in. So each Wi of T is e to the DIT times the initial value, which would be like Wi of 0, whatever that is. And then integral from 0 to T of e to the di t minus s ci of s ds. So now each of the individual transformed unknowns we have. Now, how do we get the initial values of these? We'd have to take our initial conditions for y and our original source term b and multiply both by p inverse. And that's what we'd have here. Any questions about getting up to this point? Okay. So now the goal is, how do we get from here to an expression for y of t? So what I need to do is, it's best to work, it's easiest to work in matrix vector form, but here I have each one of these written out as scalar equations. So I need to find a way to express this as a vector equation, so that I can do operations on it like I did here. So the way I could do that is using like diagonal matrices. to account for these exponentials. So I'll leave that one here, since I'm going to need that. Okay. So now I can say that, so I can rewrite that same set of equations as W of t is equal to a diagonal matrix d1t e to the d2t e to the nt times the initial vectors w0, and then plus, we go from 0 to t, and I'll have similar diagonal matrix e to the d1 t minus s e to the d n t minus s, all times c of s. Now, those diagonal matrices I can write as matrix exponentials. That's like e to the capital VT. And here I have e to the capital V t minus s. Where I can use one of the formal definitions of a matrix exponential as a Taylor series. Okay. And in this case, things work out really nicely because these are diagonal matrices, so really, it's like I'm taking a Taylor expansion of each of these individually and putting them in diagonal matrices. So that all of these are easy to work out because they're all diagonal. So E to a diagonal matrix is also a diagonal matrix.
This is the sum. Wow, God. That's the only part that's got me now.
Of this?
It's just the summation stuff, yeah.
Okay, so identity plus dt plus 1/2 dt squared, and so on.
Okay. I mean, yeah, I guess I can see like once you,
Yeah. But then if I were to write out each of these,
yeah,
like the 1 entry would be 1 plus little d1t plus 1/2 little d1t squared, and so on.
right.
But that is a Taylor expansion of e to the d1t that you see there.
Okay, yeah, this is helping. Let's see. So that's And then with the matrix, that is what that is. So you're gonna have one for each of the.
Yeah.
Okay.
Okay. Now, that's W, but I want Y. Now, W was defined to be P inverse Y. So Y is multiplied the opposite way. Y is equal to PW. Okay. So now I need to write out what that is. Term by term. So P e to the dt. And I'm going to use the same trick that I did earlier, where I have P inverse P as identity. Okay. Now, but this turns out to be e to the at, and then p times w is y, so that's y of 0. Plus, and I go from 0 to t, and this is e to the a, t minus s. And then I have, now c was defined to be p inverse b. Go the other way, b is equal to p times c. So you're just rearranging that equation. So I'll just write down. So c equals p inverse b. Therefore, pc is equal to b. So now, so this is our solution formula. And it has the exact same appearance as for a single equation, whereas in a single equation you just had a scalar exponential, like e to the pt. But other than that, exactly the same. Questions about this?
I might have to sort through some stuff later.
Okay. Now there's one thing that I kind of glossed over, and since I have time, I can be a little more rigorous about it. Because here to have the definition of the exponential. Now, I've used it here for a diagonal matrix, but it actually holds for any matrix. But how is I able to go from here directly to here?
So you said the P's were
P is some invertible matrix.
right of constants.
Yeah, they don't depend on T. Yeah, any matrices that we have here are constant matrices. But I want to take a little time to justify that, because e to the at has the same formula. Okay. But if I look closely at a to the kth power, well, that would be a is equal to p dp inverse multiplied k times. But But can you see how this product is going to simplify?
Okay, so when you're multiplying all of those together, your P inverse P's are all gonna cancel between.
Yeah, all the ones in the interior will cancel.
Mhm.
Only the ones on the outside will remain. So a to the k is p d to the k P inverse. So I can write this as a sum P dt to the k P inverse over k factorial. And the P and the P inverse do not depend on k. So I can factor those out of the sum. So ultimately what you get is P e to the dt P inverse. So that's what allows that to happen. Now, I made this big assumption at the beginning that A is a diagonal matrix. No, not diagonal. Diagonalizable matrix. That's why the decomposition PDP inverse exists, but it does not always exist. So I do need to address the case of where A is not diagonalizable, and because the goal is to arrive at this same solution formula, and we actually do, but I haven't justified that yet. For solving higher order ODEs, in certain cases, you do get a non-diagonalizable matrix. So that's an important case. I can't gloss over it. So that's what we'll look at next time. And it's going to be a pain, but
Will we work on real examples of these eventually?
eventually, yeah. Well, yeah, 'cause what I want to do is work with specific matrices tied to these higher order equations, where we can work out in greater detail what do the exponentials look like. So then you can tie it back to those ODEs and see how the solution formula is taught in introductory ODE classes come from that. That's my nefarious plan. We'll see how long it takes. All righty. Oh yeah, it's 4:59. So okay. And good luck with the homework when you get around to it. So. But no rush, trust me. Yeah, I'm gonna have 560 homework ones to grade pretty soon. Yeah. Okay. So unless you have any questions, I'll see you in a half hour.
I'd rather work this homework than create a cellular operation.